Hey Ramblers! This video covers chapter 6.1 in our textbook and deals with antiderivatives graphically and numerically. Now you may recall that this textbook likes to handle any concept from four different directions. We like to think of things numerically, graphically, algebraically, and verbally. Well, we're going to talk about antiderivatives algebraically or analytically in the next section. So this time we're just going to talk about or think about antiderivatives from a graph and what can we learn about an antiderivative just by looking at the graph. Before getting into that, it might be worth taking a little bit of time to review the fundamental theorem of calculus, which is where all this talk about antiderivatives started. Then we'll move on to families of antiderivatives, because you may recall that when we took the derivative last semester, the constant disappeared. So as we try to work backwards, where does the constant appear from? So what we'll see is we run into things called a whole family of antiderivatives. And without some more information, we really can't be sure exactly what the antiderivative is. Then we're going to take a look at how we can determine what the graph of an antiderivative looks like just by looking at the graph of the derivative. And finally, we're going to compute the actual values of the antiderivative using the definite integral. Ramblers, there is a lot of information in this video and a lot of really important and tricky techniques that you have to get used to. So please pause often, give yourself lots of time to understand this and have it sink in. And of course, thanks for watching. Okay, let's recall the fundamental theorem of calculus. And that said that if the derivative of some big f of x was equal to little f of x, or if you'd like, you can think of it this way, that big F prime equals little f, then this is true. The integral from a to b of little f will equal big F of b minus big F of a. So let's think about that just for a second. That makes little f of x the derivative, and big F of x the antiderivative. So what we're going to be doing for the rest of the year is starting with little f of x, or if you want to think, we're going to be starting with the derivative. And we're going to be working backwards in order to find the antiderivative. Okay, let's start with the statement that x squared is the antiderivative of 2x. That is to say, if we took the derivative of x squared, it would equal 2x. And we learned that first semester, and I'm sure there wouldn't be any argument at this point. But how do we go backwards? Well, if we're looking at the integral, but notice I don't put any limits. I'm just going to put the integral of 2x dx. That means, what is the antiderivative? And you could say that, all right, that's equal to x squared. And you'd think, we're done. And to some degree, that's correct. But how about this? Suppose I were to take the derivative of x squared plus 2. Well, using the techniques and the power rule that we learned first semester, that would just also equal 2x plus 0. So that would also equal 2x. So which is it? Does the integral, or I should say the antiderivative of 2x equal x squared, or does it equal x squared plus 2? And you could go on. I could say that the integral of 2x dx could also equal x squared minus 2. See, it's really unclear because the constant in each of these cases drops out. When we take the derivative, the constant has a slope of 0, and so it drops out. So what we say instead is that we have a family of antiderivatives. And so the antiderivative of 2x is going to equal x squared plus c. And c can be any positive or negative constant. And that's what we mean by families of antiderivatives. That the derivative, or I'm sorry, the antiderivative of 2x will equal x squared plus c, where c is any positive or negative constant. Let's take a look at the graph f of x equals e to the negative x squared. And that graph would look something like this. It's going to hug the x-axis, and then beginning at 2, it begins an ascent toward a maximum at y equals 1, and then it begins to decrease and then once again hugs the x-axis off to infinity. And this is the derivative of something. Could we sketch a graph of the function that this is a derivative? In other words, this is the derivative. Can we sketch the antiderivative? So take a minute and see if you could do that. Just kind of picture it on your own. Remember, the y values here are the values of the slopes. So what would that mean? The y values are very low. They're close to 0. So the slopes are close to 0 here at -2. And then near 1, the slopes are at their greatest level. And then back to out at 2, the slopes are once again approaching 0. So take a minute, pause the video, and see if you can't sketch a graph of what that function would look like. A possible solution is this graph here on the right. As you can see, to the left of x equals 0, the function has a very low slope, about 0. But then as we get close to the origin, the function begins to increase. And that's indicated by the y values of the graph on the left. You can see that the y values begin to increase. So that means the values of the slope begin to increase until they hit a maximum there at 1. And from there, the values of the slope is still positive, but the values are decreasing. So the function is still increasing because its slopes are positive, but the increases are getting smaller until once we get out near 2, the value of the slopes are near 0, and you can see that the graph is flattening out. Now, let's also notice what happened here when there was a maximum on the derivative. We had a point of inflection on the antiderivative. And that's an important distinction, an important thing to remember, that maxes and mins on the derivative are inflection points on the antiderivative. Now, it bears mentioning that you'll notice there are no y values on the axis. That's because when we are considering the antiderivative here, as we saw earlier, there's a whole family of antiderivatives. So this function on the left could be the derivative of many different antiderivatives that could look something like this, or even higher on the y-axis, or maybe lower. That all of these functions, we don't know what this plus or minus c is. This y-intercept each time would be the c. Let's take a look at an easier example and to make a little more sense of that. Okay, recall from earlier in the video, we said that the derivative of x squared plus 2 was 2x. The derivative of x squared plus 5 was 2x. The derivative of x squared minus 7 was 2x. So the antiderivative of 2x, that is if we go backwards, we see that the antiderivative of 2x equaled x squared plus c. So if we're going to look at the graph of the derivative, if we were to look at, this is just the graph of f of x equaling 2x, and we try to create the graph of the antiderivative, we would have to recognize that we do not know which of these out of the infinite number could be the actual antiderivative. So I could sketch that as my antiderivative. Maybe big F of x just equals x squared. Or maybe big F of x is up here, where it's x squared plus 5. Or maybe big F of x is down here, where big F of x equals x squared minus 7. We really can't tell when we antidifferentiate. So we just have to recognize that we can't tell what the y values are unless we have what's going to be called an initial value. And we'll look at one of those in the next problem. Okay, I took this example right out of the book. So this is the example that's on page 321 if you wanted to take a closer look at it. But it tells us that this figure, 6.7, is the graph of the derivative of a function f of x. So this is f prime, and we're going to try and figure out what big F of x looks like. I wish they'd use consistent notation throughout, but they don't. So this is f prime, or little f, and we're looking for big F. We're told that f of 0 equals 100. So f of 0, that's not f prime of 0. That's the value of the antiderivative equals 100 when x equals 0. Now please don't be confused. That doesn't mean that this value here is 100. That's obviously not. We're saying that the antiderivative's value is 100 when x equals 0. So can we sketch the graph of the antiderivative showing all critical points and inflection points and giving their coordinates? Well, let's give it a shot. Let's think about what's going to happen to the antiderivative of this function. We can see that after x equals 0, the function increases from 0 all the way to 20, because since the derivative is positive, we know the function is increasing. Then, at x equals 20, the function hits a maximum and begins to decrease. And it decreases until x equals 30. And then it hits a minimum and begins increasing again. Now this should be very, very familiar to you because this is what we talked about during the first semester, that critical points occurred when the derivative equaled 0. Also, f of x is increasing when the derivative is greater than 0 and decreasing when the derivative is less than 0. And that's exactly what we see on the graph. It's increasing from 0 to 20 because the derivative is positive, and then decreasing from 20 to 30. But what we're bringing in this section that's different than the previous chapter is now we know that the original function f of 0 equaled 100. So as x increased, we're going to add the value of this area to 100. And then we'll begin to subtract the value from when the derivative goes below the axis. Let's take a look at that. Let's review, because it's really important. This is the graph of f prime. And we know that f, which is of course the antiderivative, at 0 equals 100. So since the derivative f prime is positive, we will add all this area underneath the curve in order to determine the value of the antiderivative. And let's first calculate what this value is here at f of 10. Since we know we started off with f of 0 equaled 100, f of 10 is going to equal f of 0 plus the area from 0 to 10 under f prime of x dx, which we can see is just a triangle, and so that's going to equal 100 plus 1/2 the base 10 times the height 20. So we get 1/2 10 times 20, or 100. So we know that f of 0 was equal to 100, f of 10 equaled 200. Okay, now what's f of 20? Well, f of 20 is going to be calculated in the same way. We're going to start off with our value of f of 10, and we're going to add on 1/2. The base from 10 to 20 is 10, plus the height is 20 again. So f of 20 is going to equal 300. That's all of this area here. Now notice we have a maximum at 20. So there was an inflection point at 10, a maximum at 20, and then the values of the function of the antiderivative are going to begin to decrease. And that's because the derivative is negative. So if we were to calculate f of 30, that would equal f of 20 minus the area of this triangle, because you recall that areas below the x-axis are negatively signed. So that becomes minus 1/2 the base, 10, times the height of 10. Now, you can either think of adding negative 10 or just subtracting 10. It's the same thing. So we get f of 30 is going to equal 300 minus 50, or 250. So that's how we calculate the value of an antiderivative. We have to start off with what's called the initial condition, or the initial value, and then you work from there. For numbers that are, or areas that are over the x-axis, we add the values of the area under the graph. And if the value is under, or I should say the area is under the x-axis, that means that the antiderivative is decreasing. Okay, Ramblers, a lot of information in here. We'll get lots more practice in class. Thanks for watching.